But today we're going to look at complex numbers again, and we're going to look at polar trigonometric form and what happens when we multiply complex numbers in this form. So you may be wondering, well, what exactly is the point of polar trig form? And we're going to investigate this question by doing a couple of examples. So what I want you to do is, if we have z1 equals √3 plus I and z2 equals I want you to find the value of z1 times z2 and sketch z1, z2, and z1 times z2 on an Argand diagram, and do all of this in Cartesian form. If we times these together, it's actually quite nice. We'll get √3 plus I times z2, which is I. So we'll get √3i plus, well, I squared, and we know I squared by now is -1. I hope we know that. So then we get √3i minus 1, or if we write it nicely, -1 plus √3i. Z1 will be √3 units in the positive real direction and 1 unit up on the imaginary axis. And Z2 is simply I. So remember, that's just 1 unit up on your imaginary axis. Z1 times Z2 minus 1 plus √3i. So I'm going to go -1 along the real axis and √3 up, which is 1 point something on the imaginary axis. Somewhere here. Now, notice the location of these 3 points, Z1, Z2, and now Z1 times Z2. I'm just going to call that Z3. The angles each of these make from the positive real axis, and have a look at the length of each of these complex numbers from the origin. The next thing we're going to do is we're going to convert Z1, Z2, and Z1 times Z2 into polar trigonometric form on your CAS calculator. So you go to number, complex, and then convert to polar. So if I convert √3 plus I, so Z1, into polar form on your calculator, what you actually end up is what is called as polar exponential form. And you'll spit out something weird that looks like this: 2e pi on 6i. But you can use this to write it in polar trig form. The 2 will give you your r, or your modulus, and your theta will be whatever's in that exponent next to the I. So in our case, it will be pi on 6. So the polar trig form of √3 plus I will actually be 2 bracket cos pi on 6 plus I sine pi on 6. You can do the same for Z2 on your calculator. Again, it will spit out what is known as polar exponential form, and this is the form of complex numbers you'll use at university. It's just, again, a different, more succinct way of expressing complex numbers. So here I get from this, the modulus is 1, and my theta, it should be pi on 2 here, not pi on 6. So I get 1 cos pi on 2 plus I sine pi on 2. On my calculator, again, I can convert Z1 times Z2, or -1 plus √3i, into this polar exponential form. And using that, I can rewrite it in polar trig form as 2 cos 2 pi on 3 plus I sine 2 pi on 3. Okay, here's the interesting things. I want you to look at the relationship between the modulus of Z1, the modulus of Z2, and the modulus of Z1 times Z2. And the same with the argument of z1, the argument of z2, and the argument of z1 times z2. There should be a relationship. Let's start with the modulus. So notice the modulus of z1 is 2, and the modulus of z2 is 1. Interestingly enough, when I multiply r1 and r2 together, or 2 times 1, I will always end up with the modulus of our complex number z1 times z2. In this case, it's 2. And in this case, that is what we got in our polar trig form. So when you have two complex numbers and you times them together, you can simply times their modulus together to get their new modulus. What about the argument then? Let's look at our argument of z1, that's pi on 6. The argument of z2 is pi on 2. What can I do to both of those to get our new modulus of z1 times z2, which is 2 pi on 3? Have a think. So this one's a little different. If I add theta 1 and theta 2, hopefully you've noticed that you will get our argument of z1 times z2, which was 2 pi on 3. So a shortcut. When you're multiplying two complex numbers together, you can find the new argument simply by adding the arguments of each respective complex number that you're multiplying together. The point is a shortcut. So when you multiply two or more complex numbers, you can take a shortcut by converting to polar trig form. And then, if you're multiplying the numbers together, you multiply the moduli of these numbers together and you add their arguments together. The way I remember this is multiply the moduli, m and m, and add the arguments a and a. So an example of when this might be useful is if you take a complex number to a high power. So if I ask you, what's 2 cos pi on 6 plus I sine pi of 6 all to the power of 5? Well, here all I have to do is multiply the moduli together. So I'd have 2 cis pi on 6 is to the power of 5 is really timesing it by itself 5 times. So I would take the modulus and do 2 times 2 times 2 times 2 times 2, 5 times. And I'd take the argument and I would add these together again 5 times. So pi on 6 plus pi on 6 plus pi on 6 plus pi, all the way 5 times. So then I get the complex number of 2 cis pi on 6 all to the power of 5 is really just 2 to the power of 5, and then cos 5 pi on 6 plus I sine 5 pi on 6. That is much easier than me trying to write this in Cartesian form and then multiplying it by itself 5 times. Similarly, when we divide complex numbers, we divide the moduli and we subtract the arguments to get the new modulus and the new argument of z1, say, divided by z2.